Deep learning enables a vast range of use cases in audio processing, such as improving situational awareness for autonomous vehicles, smart speakers, and hearing aid systems. However, a natural issue in the field of smart audio is that very often the devices that would benefit the most from these advances are edge devices. Deep neural networks often consume more computational resources than these devices can offer. To improve the efficiency of these networks, we start by reconsidering how much computation is required for a neural network to function. We tend to think of the weight parameters as real numbers, but in reality, these are 64-bit binary numbers, one of 2 to the 64 possibilities. This is where we ask the question, do we really need 2 to the 64 distinct possible numbers? Would 2 to the 32 suffice, or less? Taking this to the logical extreme, we have the process of binarization. The next step was to apply binarized networks to a real-world problem and see how it performs. The problem we set out to solve was to binarize a sound event detection system, which not only classifies sounds, but also detects when the sounds start and end. It's common for the sounds to overlap and interfere, creating a highly complex problem. The system works like this. First, take in the sound wave and apply a Mel frequency transform. We can think of this as a way to convert the audio recognition problem into an image recognition problem, allowing us to utilize convolutional neural networks. A series of convolutional and max pooling layers proved effective at approaching the state of the art for this problem. Next, we binarized the network and looked into ways to improve the performance to be comparable with the original system. The first issue with this is training. How can we make small adjustments to the parameters if the parameters can only take one of 2 values? We found the most effective optimization strategy was the binary optimizer, which works like this. First, calculate the gradient as if the weight were a continuous real variable. Repeat this for many samples, taking a weighted average of the gradient called momentum. We change the binary weight only if the momentum is sufficiently high and the gradient points in the direction of change. Having chosen our optimizer, we tuned our hyperparameters to get the best out of our binarized system. We've been able to demonstrate a favorable accuracy-performance trade-off. Our model takes up 96% less memory than its full precision equivalent, runs inference up to 44% faster, and provides all of that with just a 2% performance drop-off. We hope that this can motivate further research in this field and help overcome the limitations of deep learning in audio devices.